I've already covered what is a galvanic cell, so let's do a brief recap. Okay, so a galvanic cell refers to a spontaneous redox reaction that will convert chemical energy into electrical energy. Okay, and this is a very important topic nowadays because if you realize within the next 5 or 10 years, you will see electric vehicles running in Singapore or on the roads of Singapore. So that electric motor, right, actually uses the galvanic cell where the current will drive the electric motor. Okay, for those that are not very in tune with cars, the engines that are in our cars nowadays are called ICE, internal combustion engines. So the fuel undergoes combustion, then the heat energy produced will cause the expansion of gases that will drive the pistons of our ICE. Okay, and then somehow the axle will then turn the wheels and the wheels will drive the car forward. Okay, so for this, we learned that anode is where oxidation occurs and cathode is where reduction occurs. Okay, you also need to know the polarity of the electrodes. In a galvanic cell, the anode is negatively charged while the cathode is positively charged, and the electrons will flow from the anode to the cathode. Okay, I've also introduced what is standard electrode potential. So standard means standard conditions. What are the standard conditions that has been introduced in lecture 1? They are 298 Kelvin, 1 bar, aqueous ions, the concentration must be 1 mole per dm cube. And then if you ever see this superscript, it will represent standard conditions. Okay, and then for the electrode potential, they are also known as reduction potential. You look at the data in the data booklet, you read from left to right. So it will appear something like this. So when you read from left to right, it is reduction. If you read from right to left, it will be oxidation. Okay, so what is the significance of the value for the electrode potential? A positive E value will mean reduction is favored. A negative E value will mean oxidation is favored. So I've also introduced to you the 4 factors that will affect the E values. They are what? Pressure, temperature, what else? Which are the more important ones? Concentration. So that's why we have defined all of these standard conditions. Okay, and then the E value for a half cell must always be measured against a reference electrode, and the reference electrode is your SHE. Okay, this is your reference electrode. Okay, so I've also introduced you the 3 different types of half cell. Okay, please go and revise. Okay, so for today's lecture, we will make use of the E values to see how they are applicable to oxidizing and reducing agent. We also need to compare further how we can make use of the E values, and by making use of these E values, we can calculate the voltage of a galvanic cell, okay, under standard conditions. And then what is the mathematical relationship between the change in Gibbs free energy with the electrode potential of a galvanic cell. Okay, that's what we are going to cover today. Yeah? Okay, the E value that you have in the data booklet or in this set of notes, please recognize that the E values is independent of the electron transfer. So I think it's easier if you look at the example at the bottom of this slide. Even if I multiply by 3, right, you realize that the E value or the standard electrode potential values remain the same, which is plus 0.34 volts. Then I think the curious students here will ask me why, but the physics students should be able to answer me. Okay. Okay, the reason is how do we define voltage? The physics student will tell me that the units or the SI units, sorry, not the SI units, the units is joule per coulomb. So even if I times 3, which means I move more electrons in the complete circuit, the energy expended to move the increased number of electrons will also be affected the same mathematically. So I need to times 3 again. So because voltage is joule per coulomb, right? The times 3 in the numerator will be cancelled out by the times 3 in the denominator. Okay, so if you follow me, it's okay. If you don't follow me, it's okay because they will test you why is it independent. Okay, but the physics student should be able to appreciate why the E value doesn't change if you times 3, times 2, times half or whatever. Okay, so the outcome is, or the conclusion is, the voltage remains the same. Now, this is an example of what you will see in your data booklet. This is not exhaustive because if you flip through your data booklet or your current set of notes, you realize there are many pages. So this is just one example. Okay. So what is the definition of an oxidizing agent? The ability to oxidize the other species in a equation. So when you oxidize the other party, you yourself is reduced. So why I say the species is on the left hand side? Because if you look at your data booklet, you read from left to right. Left to right is a reduction. And for those that are quicker in their thinking, a good reducing agent will have a positive E value. Because remember at the start of this lecture, I say the more positive the E value, the more favorable the reduction process is. Okay, so if you have a more positive E value, it means that the species that appears on the left hand side is more readily to be reduced, and therefore it will be a strong oxidizing agent. Okay. If we are talking about reducing agent, right? Remember, a reducing agent is something that will be oxidized, correct? Not? So if you are talking about oxidation, we read from right to left. I repeat, you read the equation from right to left. That's why on this slide now you say the species is on the right hand side. Okay. So for a good reducing agent, the more negative the E value, the merrier. It means that when you have a negative E value, the least likely reduction is to occur, which means oxidation of that species is more likely to occur. So the conclusion is, if you are looking for a strong reducing agent, you should look for a more negative E value. Okay. Okay, let's look at one example. You should be able to tell me by looking at the data booklet which is the strongest reducing agent. Who can tell me? What's the strongest reducing agent? I will just give you the first one. The strongest oxidizing agent, you will do it as a homework, but I will not give the answer. You should ask your friend and see whether you arrive at the same answer. So the first one should be K, because it is most positive E value. Okay, so for the strongest oxidizing agent, you should look for the most negative E value, and please go and hunt for it and compare with with your friends. Okay. Okay. Now we will try to arrange the following species here in terms of their oxidizing power. Okay. So when we are talking about oxidizing power, we are talking about oxidizing agent, OA. So if you have been following, if you are a powerful OA will mean more positive E value. Can see? Correct? So what we need to do now is to look for all these species from your data booklet. Br2, Cr2O72 minus in H plus acidified, Fe3 plus as well as H2O2. Then I will need to tell you, you don't just look for all these species. Because we are talking about oxidizing agent, right? Oxidizing agent is reduced when they are functioning as oxidizing agent. Should you look at the left-hand side or the right-hand side in the data booklet? The answer is you should look at the left-hand side. Okay. Okay, more positive E value. So left-hand side, PR2 1.07, 1.33. Okay, so far so good, all positive, which means they like to be reduced for BR2 and CR2O72 minus. We still have another two species, which is on another slide. So let's continue. So, which is the one that is the wrong one? Make a guess. They must appear on the left-hand side, right? Remember I was saying for oxidizing agent, they like to be reduced. So we cannot choose the one at the top for Fe. Okay, so we pick out all the relevant equations to compare with the values there. So in here, there is one that is 0.77, one is 1.77. So we can write it down. So we write all of them down and start comparing, right? So I have 1.07, 1.33, 0.77, 1.77. So who are the biggest positive value and which one is the smallest positive value. So I will look at these two first, correct? One is the most positive, one is the least positive. So basically the answer is quite obvious already. H2O2, because it's the most positive at plus 1.77, it is the most powerful oxidizing agent here, while the smallest, what do you call it, least positive value plus 0.77 will mean that Fe3 plus is the weakest oxidizing agent here. So these are my two extreme ends in the scale that I want to create in terms of increasing order of oxidizing power. Okay, so most positive, then this one least positive, then I have the arrangement of all these species in terms of oxidizing power. Okay. Okay, let's continue. Checkpoint 3. So checkpoint 2 was about oxidizing power. Now we are looking at reducing power. So reducing power, we are talking about reducing agent. So reducing agent, do we want the E value to be more negative or less negative? Reducing agent means you yourself will be oxidized. So if you want to talk about more powerful reducing agent, that means I want more negative value. Okay? And because we are talking about reducing agent, we are looking on the right hand side. That means we read the reversible equation from right to left. Because after all, a reducing agent is oxidized. Okay? So we will need to look at the data booklet now. Okay? So most negative E value. Okay, remember just now I was saying we need to look at the right hand side, right? Because we read from right to left, oxidation now. Okay, because reducing agent, it itself must be oxidized. So, okay. So these are for Cu and Fe2 plus. So we note the value plus 0.34 and plus 0.77 for these two. Okay. Okay, any questions or not? Why did I choose 0.34 instead of 0.52? The reason why I choose 0.34 is because that is the more negative value or the least positive value. Because I say I choose the stronger Ra, reducing agent. Why did I choose the Fe3 plus to give Fe2 plus? Is because I need to read from right to left. A reducing agent itself must be oxidized. Okay, so I choose the 0.77. Then the others are quite easy. So I listed down all the standard electrode potential values here for you. How do I arrange them now? The question is about increasing, reducing power. So if I want strong reducing power or strong reducing agent, I would like to be as negative as possible for the standard electrode potential. Okay, so minus 1.66, the least negative one, which also means the most positive one, will be the weakest reducing agent. And finally, that will be the order. Okay. So from these two checkpoints, you have learned how to arrange species as stated in the question in terms of their reducing power and oxidizing power based on standard electrode potential values. Okay, so more positive E value means more easily reduced. More negative E values means more easily oxidized, and you need to relate them back to oxidizing power and reducing power. Okay, application. Okay, let's continue. Okay, we can also make use of the E values to help us to prepare ions in water and to ensure their stability. What do I mean by that? Okay, so we have this Fe3 plus reducing to form Fe2 plus. And if you look at this value here, plus 0.77, means the reduction is favorable because it's positive. But if I change it to alkaline medium, it has become negative, which means the reduction is now unfavorable. Okay, so can we fill in the blanks in this sentence? Fe2 plus is more stable with respect to Fe3 plus in acidic medium. Okay, then in alkaline medium. Because plus 0.77 means that the reduction of Fe3 plus to Fe2 plus in acidic medium is favorable. But if you use an alkaline medium, it becomes negative. Okay, so if you want Fe2 plus, you should use acidic medium. Which means that the last blank to be filled is Fe2 plus can be stabilized against oxidation by adding acid. Okay. Okay, let's continue. When you combine two half cells together to get a galvanic cell, we need to know what is the voltage of this galvanic cell that you have created. I think when we say the word galvanic cell, it's still quite foreign to you. Maybe I should use the word battery. A battery is actually a galvanic cell, okay? So what is the most important invention, or I should not say most important, one of the most important invention nowadays is your lithium ion battery, right? You know the battery that you power your handphone, they are all lithium based, correct or not? And lithium is a metal that is not found in great quantity. So now, if you read the latest news, right, China has created a sodium-ion battery, but I don't know how workable that technology is. So we will see whether next time whether the lithium-ion battery will be replaced by a sodium-ion battery. Okay. Okay, so the equation that you need to know is the one that is boxed in red. This one. So if you have two half cells that are combined, connected together, I would say combined together, connected together using external wires and a salt bridge, can we calculate the voltage of this galvanic cell or this battery? We use this formula, reduction minus oxidation. So we need to look for the values in the data booklet to help you. Okay, so let's continue with an example or a drawing. Okay, so this is a galvanic cell that is created using two half cells, which are just circled in red. You can see, right? One of which is copper, involving the element copper. The other one is involving the element of magnesium. So in Sec 3, Sec 4, right, you have learned something relevant for this particular topic called electrochem. Do you remember your teacher asking you to memorize a phrase, what, please, what, keep, what, don't know what, cats and dogs, don't know what, in cage, something like that, you know? I cannot remember because I don't bother to memorize really, but I know there is such a thing. So the first is, it represents the most reactive metal, I think, is potassium, right? Then the last one or the least reactive is gold. Okay. Then you have hydrogen somewhere in the middle. Then what is the significance of this memory work is that if you have a metal or element below hydrogen, right, you can actually use hydrogen for displacement reaction. Remember that is it the topic called metals, I think, or reactivity series? I can't remember. But anyway, we don't need that now because we have these values to help us. Can see or not? So for magnesium, in comparison to copper, right, magnesium is more electropositive. That's why it has a negative value. Can see or not? Because negative will indicate that magnesium prefers to be oxidized. But copper, if you realize, it is positive. So copper 2 plus prefers to be reduced. Okay. So coming back to this lecture, we will make use of the formula now. How to calculate the voltage of this galvanic cell that is formed by combining these two half equations. Okay, and by virtue of the standard electrode potential, more positive means that reduction takes place at the copper half cell, while oxidation takes place at the magnesium half cell. And then how to calculate the voltage? We make use of this formula, reduction minus oxidation, and we can get the voltage plus 2.72. I need to caution, remember this superscript here. What does this superscript stand for? Standard conditions. Which means that if you combine the same two half cells, but you carry out under another set of conditions, it will not be 2.72. Okay, this 2.72 volt is only for standard conditions, okay? Okay, so you should have the ability to combine the two half equations and write the overall equation. And this one is easy because the two electrons and the two electrons will cancel out perfectly. But what if the electrons doesn't cancel out perfectly? What do you need to do? You need to do something called LCM. You know what's LCM? What's LCM? Lowest common multiple, okay? Okay, so I think it's easier if I go through a checkpoint so that you know how to apply this. So what if you have two half cell again? you have an iron half cell and a nickel half cell. So what's the first thing you do? Look at your data booklet. Okay. Now, minus 0.44 and minus 0.25. Who is the one that likes to be reduced and who is the one that likes to be oxidized? The more positive one likes to be reduced. The less positive or the more negative one likes to be oxidized. So you should immediately tell yourself that. Okay, then after that, you write down the two half equation and then you combine the two half equation. So this one will be OX. This one will be RED. And together, you should know since Sec 3 and Sec 4, they give you the word called redox. Then the 2 electron and 2 electron cancel out, right? You get your overall equation. You can make use of the formula to calculate the voltage of this galvanic cell under standard condition. And then you should know where is the anode and where is the cathode. And the electrons will flow in the external wire from the anode to the cathode. Okay. Easy, right? This one, this topic. Okay, let's continue. Okay, I will just show everything in this slide. I think it's quite straightforward. When an E naught cell is positive, it means that the reaction is spontaneous. If an E naught cell is negative, it means the reaction is not spontaneous. Okay, and if the E naught cell is zero, it means that the redox reaction that you're talking about is in equilibrium. Okay, now in physics they learn that when there is a voltage in physics is also known as EMF, which stands for electromotive force. Only when there's an electromotive force can a current flow in a complete circuit. Okay, so when you have a potential difference, that means there's an EMF, then a current can flow. Okay, so when there is an E naught cell and it's a positive value, you have set up a potential difference that will allow you to move electrons from one place to another in a complete circuit. Okay, we need to relate, which is one of the things we are aiming to do today, the E naught cell to change in G. What is change in G? Change in Gibbs free energy. And there is this equation that you need to learn. Change in G equals to minus NFE. N is the number of electrons, F is a constant, which is the Faraday constant, and E is the electrode potential of your galvanic cell, the voltage of your battery, or the voltage of the galvanic cell that you have set up. Okay, so what is the significance of this equation? It will be reviewed on the next slide, which is, I think, easier to understand. So basically, if you do a quick mathematical calculation, right, if your E naught cell is positive, your change in G will be negative. If your E naught cell is negative, your change in G will become positive, right? It's simple maths because one is plus, positive times negative. The other one is negative times negative, okay? So I will show you the table form which is more accessible. So which topic you learn, right? E naught cell positive means it's spontaneous. When E naught cell is positive, it means the change in G negative, also spontaneous. You can see or not? So they are actually the same thing. Okay. Change in E negative, which means change in G is positive, not spontaneous. Okay. Okay, so the E naught cell, remember this superscript I was talking about? This one represents standard conditions. So the voltage of a galvanic cell or a battery will change if you change the conditions for like pressure and temperature. Okay. Which means whatever value that you take from the data booklet is only accurate for standard condition. So like the example I gave at the start of the lecture, electric vehicle, right? So the voltage that you calculate for the battery in the electric vehicle may not be true in real life because in a car, the operating temperature of a car is definitely not standard condition. The reason is very simple. An engine has moving parts. When something has moving parts, the temperature by right will get higher, right? You get the idea now? So whatever values that you take from your data booklet, right, will not apply to real life, let's say in electric vehicle, because the temperature definitely will be very different, okay? So the voltage may decrease or increase depending on your temperature. Okay, another thing is that the E values or the E naught values only tells you whether a reaction is spontaneous or not. Spontaneous means you only consider it from the thermodynamic viewpoint. It doesn't tell you anything about the speed of the reaction. The speed of the reaction is related to another topic that you have covered in JC1, which is your reaction kinetics. Okay, I know some of you hate that topic, but speed of reaction and whether a reaction is spontaneous or not under H2 Chem is two separate topics, but H3 students will know that actually there is some effect on one another, but we will not go into that. But we take it that these two are two separate topics, okay? Okay, now we are coming to another part of question that we need to learn. Okay, before we cover this question, right, I just want to highlight something. Whatever we are learning now has something to do with redox reaction, correct or not? What is redox? It is made up of RED and OX. That means reduction and oxidation has to occur in tandem at the same time. Okay, in tandem means they must occur together at the same time. So for I2 in water and Fe2 plus in water, what we are assuming here is we need them to participate together in a redox reaction. So maybe we start hunting for the information from our data booklet, and we have 0.77 and 0.54 here. And when this question say a mixture containing I2 and Fe2 plus, right? What you should interpret it as, they must be the reactants in the overall equation. That means I2 must react with Fe2 plus. Okay? So one of these species here must be undergoing reduction, and one of these species here must be undergoing oxidation, right? Then together they can become redox. So if you look at the two half equation here, one of them appears on the left hand side, the other ones appear on the right hand side. Why? Because we must have both reduction and oxidation happening. So you cannot have the two parties all appearing on the same side, because there is no such thing called red or OX. You know what I'm saying, right? Okay, then you will never learn something called redox already, what? If it's called red or ox, there's no such thing, right? Never hear before, right? Okay, so you will be able to calculate the E0 cell for this battery under standard conditions. I always highlight the word standard conditions, because what you have here is a battery that doesn't give you a voltage. It is negative. It's a non-spontaneous reaction. But it doesn't mean this battery cannot work. It may work if you change, let's say, the concentration of the aqueous species, you change the temperature, you change the pressure, because pressure will affect gases, so pressure doesn't affect here. Okay, but anyway, it may work, but under a different set of conditions. Okay. So the reaction under standard condition for this redox reaction is non-spontaneous. Okay, so we cannot have red or ox. We must have redox. Okay, let's continue. Okay, a mixture that have I2 and Fe2 plus. What we are trying to say here is actually what I've said in the previous slide. We cannot use the last one, which I cancel out in a blue line, because we cannot have red or ox. Okay. So we reject the one that I've cancelled out in a blue line. Understand? Okay, another example. Cr2O72 minus and I minus. We try to look for the relevant half equations. Then we check, are they on different sides of the half equation or not? Okay, very good. One on the left hand side, one on the right hand side. Redox can happen. Then we need to check again. Is the E0 cell a positive value? Yes. So the redox reaction is spontaneous, and I hope that you can write the overall equation or the overall redox equation, because this one needs to calculate LCM. What's the LCM? When you have 6 and 2, come, someone just shout out the answer. Hey, what's the LCM for 6 and 2? 6, understand or not? So basically, this one need to times 3, then this one becomes 6, then this one becomes 6. Then you can do the cancellation of the 6 electrons. Okay, then you'll be able to form the overall redox equation. Okay, let's continue. So we will have another example where you have Fe3 plus in water and Br2 in water. So I will hunt for the information from your data booklet, and do you start doing the calculation now for the voltage? What do you think is the answer? The answer is no. Why? Because both species occur on the left-hand side. We cannot have a reaction that is called rate. Understand or not? We cannot have a reaction that is called rate, right? It must be redox, right? So there is actually no need to calculate anymore. Okay, so this is a trick question. Oops, I cannot go back. But basically, you just remember, because I'm recording, I cannot go back. But anyway, that one is a trick question, okay? There's no need to calculate because you cannot have reduction and reduction happening at the same time. I clicked too fast, okay? But anyway, you go home and pause that, understand or not? Anyway, this is the last slide. So what have we learned today? A more positive electrode potential value will mean that it is more easily reduced. So it will be a strong oxidizing agent. Okay. A more negative electrode potential values means that the species is more easily to be oxidized. It will be a strong reducing agent. Okay, and you need to know the mathematical relationship. Change in G equals to minus NFE. And when E naught cell is positive, it means it is a spontaneous reaction. And finally, you need to know how to calculate your E naught cell. Reduction minus oxidation. Okay, so that is all from me today. And that is end of lecture 2. I will upload lecture 2 tomorrow, and tomorrow I will also upload lecture 3 recorded. So that will be the end of Electrochem part 1. Okay, thank you.